Hello children. Okay, so we are continuing current electricity. So today's topic is electrical energy and electrical power. So we have covered how to deduce the combination of resistances, and we know how to calculate voltage, current if we get a circuit. We have studied nodal analysis, mesh analysis, all these basic stuffs. Now when we need to calculate electrical energy or electrical power, we may have to use those concepts here. We have studied about cells, combination of cells, what is charging of a cell, what is discharging of a cell, all these things we have seen. So those basics will come here and there when we discuss this topic also. Okay, so electrical energy and electrical power in a circuit or in a part of a circuit, or what is the power in a battery, power delivered, power absorbed, who is absorbing power, or we can say who is dissipating the power, who is giving power to the circuit. Okay, all these things we will discuss today. So take down electrical energy and electrical power. Okay, so we will build the concept slowly. Battery is discharging. Okay, so when battery is discharging, current will be entering through negative terminal or positive terminal. Whenever battery is discharging, we have studied already, okay, the current will be delivering from the positive terminal. So this is what is discharging of the battery, or battery is discharging. If we are charging, then current will be entering through the positive terminal. We will keep a big battery in order to charge this battery. Okay, so what we can say? We can say suppose if voltage of this battery is V, suppose if the voltage of this battery is V, this is nothing but potential difference. So can we say this is V, this is 0 volt, this is V volt, this is V volt. Suppose if the voltage difference is V, then we can say this is V volt, this is 0 volt. So I'm just removing the unit, I am writing V and 0. So it is understandable, right? 0 volt and V volt. So can I write here also 0? Here I can write V. Okay. Current is passing in this direction. So can I say charge is moving in this direction? A small charge, suppose if we consider a small charge dq which is passing through the circuit, can I say dq charge is moving in this direction? Time taken for the charge to reach from this end to this end, let it be dt. Okay, so what is energy here in this case? Okay, in order to shift this dq charge from this end to this end, this battery will have to do some work, okay, to move charge dq across the circuit. A work dw, okay, a work dw has to be done by the battery. Correct? In order to move a charge dq from this point to another point, okay, just considering 2 points, a work dw will have to be done, okay, will have to be done by the battery. Correct or what? Okay, now you have studied about potential also, electrostatic potential. What is electrostatic potential? The work done in order to bring a charge from infinity to a point. Suppose if we are discussing about the potential of a point, what we used to say? The work done in order to bring a charge from infinity to this point. So work done per unit charge, is nothing but final potential minus initial potential, or potential at the final destination or final point minus the potential at the initial point. We have studied this. So same concept we are doing here. The work done in order to bring a small charge, a small work done. So dW by dQ is nothing but the potential at the final point minus potential at the initial point. So V minus 0 I can write. Clear? V minus 0. So this is nothing but final potential or final point potential minus initial point potential. Okay, so dW divided by dQ is equal to V, or we can say work done, W is equal to V dQ. Clear? So this is the work done. Now how to find the potential, power? Okay, so here in order to do the work done, the battery will have to release some energy. Okay, in order to do this work, this battery will have to release some energy. So we can say this work done is nothing but the energy released by the battery. Okay, energy released by the battery. So energy released by battery. So this is a small energy for small charge, dE. If we write, this is nothing but dE is equal to, this is dW, just we need not change it. dE is equal to V dQ. Energy released by the battery. So energy is spent by the battery in order to bring this charge from this side to that side. Clear? Noted? Done? Okay, I am removing this. Okay, now what about power? What is power? Power is the rate of energy. Power is the rate of doing work or rate of energy. So we can say dW by dt. Rate, how fast work is done or how fast energy is released. So we can write dW by dt, or we can write dE, both are correct, dE by dt. So we can write V dQ divided by dt. So initial of the chapter, in the beginning of the chapter we have studied this. What is dQ by dt? Current. dQ by dt is current. So we can say power P is equal to dE by dt, which is nothing but V dQ by dt, which is nothing but V into I. So this is what is power. When the battery is discharging, or the power in the battery, or the power released by the battery, energy released by the battery is nothing but V into I. This voltage into the current that is passing through the circuit. This is the current that is passing. So remember this, understand the concept. No need to by heart, or you just no need to mug up P is equal to VI. We have already studied this in 10th class. So but understand this and study now. Next point, battery is charging. Battery is charging. So when if it is charging, then if the battery is connected like this, current direction will be towards the positive terminal. Current direction will be towards the positive terminal. This is V. The EMF or the potential difference that is created by the battery will be V. So this is plus, this is minus. So I can mark here 0. I can mark here V. So we will be bringing charge dq from this end to this end, taking a time t. So battery will have to, okay, so there should be a work done in order to bring the charge from here to here. So this work is not done by the battery, not by this battery. It is done by another big battery we connect. Okay, we have already studied this in the basics of cells or basics of battery. Okay, so again same thing, work done by the battery, okay, in bringing dq charge from this side to this side is equal to dw. So dw by dq, okay, work done per unit charge is nothing but the potential at the final point minus potential at the initial point, 0 minus V. So here this is the final point, charge is coming in this direction, this is the initial point. So we can write dw is equal to minus V dq, okay, minus V dq. So this is nothing but the work done while charging the battery. Okay, so here the energy absorbed by this battery. So generally when current is moving from the positive terminal of the battery, that battery will be supplying energy to the whole circuit. But if there are two batteries, one battery EMF is bigger than the other battery, and if it is connected in such a way that the positive terminal of the bigger battery, the battery with the better EMF, okay, that current will have to be going to where? To positive terminal of this battery. If that is the case, this will be charging this circuit. So at that time energy will be absorbed by this will be taking the energy. The battery with a better EMF will be supplying energy. So here this is going to absorb the energy. That is the reason minus comes here, but negative will not play any role. We just need to understand it conceptually, and we should be in a position to comment whether it is absorbing or releasing. If current is moving to the positive terminal, definitely this is going to be absorbing. Okay, so energy dE that is absorbed by this battery is nothing but V dq. I am removing this negative because already we are mentioning that this energy is absorbing. Okay, absorbing energy, V dq. Okay, V dq is equal to what? dw by dq, both are fine. Okay, so we can write like a V dq. Okay, now power is the rate of energy. So this is nothing but dE by dt. So V dq by dt, what will happen? This is going to be Vi. Same formula will come. Only difference is here energy is absorbed. There in the previous case, when the battery is discharging, energy will be released. Clear? Note it down. Third basic which we need to understand is resistor. So here energy will be dissipated. Energy is dissipated. Dissipated means it will be made to come out, or it will be wasted. Energy will be wasted. Actually energy will be wasted. Just understand this thing. The bulb, suppose if we are connecting in a network, that bulb is nothing but a resistor. A resistor wire will be there, current will be passing through that. So energy will be wasted there in the form of light energy or heat energy. So when the heat energy is dissipated, that it will start radiating energy. In thermal properties of matter, in the +1 topic, we study about radiation. So radiation is nothing but energy. So when the energy is wasted, actually it is radiating energy. When it is radiating, we will be getting illumination in the room. So actually that wastage is what we are making use of for our own benefit. So actually speaking, honestly speaking, energy is dissipated or wasted in the resistor, but that we will make use of it. Fan is a resistor. So all the electrical appliances, right, they are resistors only, but we will make use of that dissipation for our own benefits. Okay, so energy is dissipated in the case of resistor. So if this is resistor, okay, current will be, if it is going in this direction, then dq charge will be moving to this end. So we used to say, suppose if voltage V is wasted, or voltage V is eaten by the resistor, or we used to say voltage drop is there in the resistor. Voltage drop is there in the resistor, we say. So if V voltage is the drop in this resistor, say for example if 3 voltage is dropped in this resistor, then this side, if this is 9 volt, this side it is going to be 6 volt. Understood? If 3 volt is taken by the resistor, if this terminal voltage is 9 volt, then after 3 volt loss in this resistor, here the potential is going to be 6 volt. Suppose if this is 10 volt, after 3 volt we are going to get 6 volt. But one thing we can say, the difference of potential between this point and this point is what? 9 minus 3, 9 minus 6, 3, 10 minus 7, 3, or 12 volt minus 9 volt, 3. The potential difference is always what? Will be 3 in this case. So whatever be the potential drop that happens in the resistor, that much will be the potential difference between these 2 points. So again what I can say, I can simply write here V, I can write here 0. This means that if the potential between these 2 points, potential difference between these 2 points is nothing but V. Okay, so just for our calculation purpose, we can write, nothing wrong in doing that. With this concept only we have written VA minus E minus R minus VB is equal to 0, same concept. Okay, so potential difference we can say V and this thing as 0. So some work is done. Okay, same concept, some work dW is done in order to bring the charge from this side to this side. So work done per unit charge. Work done per unit charge is what? Final potential minus initial potential. So dW is nothing but minus V dq. So here also energy is taken, energy is absorbed and it is dissipated. So for discharging alone, battery will be releasing energy. For charging, for resistor, for all that energy they will be absorbing. So there will be reduction in the energy supplied. Energy will be supplied. Suppose 10 joule is supplied. One battery will, if it is charging, one battery will take 3 joule. One resistor will take, if total 7 joule. So total energy released will be total energy absorbed in the circuit. So dW is equal to minus V dq. So this is nothing but the energy absorbed by resistance R, or energy dissipated, whatever it is absorbed, that will be dissipated, is nothing but, okay, energy absorbed. And this energy absorbed will be what? This will be dissipated. This will be dissipated, is nothing but minus V dq, and power is nothing but dE by dt, rate of energy. So minus V dq by dt, we will be getting Vi. Okay, clear? Note it down. So resistor and battery charging, discharging. So in the case of resistor, circuit like this is V, this is 0. So the energy is nothing but minus V dq, okay, or we can say energy absorbed, power P is equal to Vi. Okay, so here if current I is passing and if the resistance is R, then we can say I is nothing but V by R. I is equal to V by R. Substituting that, we will be getting V square by R. Okay, then V is equal to IR. V is equal to I into R. So we can say I square R. So these three formulas, P is equal to Vi, P is equal to V square by R, P is equal to I square into R. So all these formulas are applicable here. In the case of battery, if it is charging, I is coming, if this is V, okay, this is V, this is going to be 0. So again, D is equal to what? V dq, V dq. Energy is released. Energy is released. And what is power P? P is equal to simply Vi, no other formulas, only P is equal to Vi. In the case of discharging, current will be moving in this direction, and this is going to be 0, this is going to be V, and charging power energy is absorbed, charging energy is absorbed, minus. So here energy dE is equal to V dq, okay, V dq, and energy is released. Energy is released, power P is equal to Vi. Clear? Note it down. So now we will see energy dissipated in the resistor. Power P is equal to Vi, I square R, V square by R. Okay, we have studied this, but this need not be always true. Okay, this voltage can change, current can change. Okay, so in those situations, what we will have to do? Okay, so we will derive that formula also. So the energy dissipated in a resistor is nothing but V dq. Energy dissipated in a resistor is nothing but V into dq. So power is nothing but dE by dt. Power is equal to dE by dt, or simply we can say if P is equal to dE by dt, dE is equal to what? P dt. So this is the energy in moving a small charge dq along the circuit. So this is the power associated with that. So what will be the total energy dissipated? Total energy dissipated will be the sum of the energies used to shift all the charges along the circuits. So that will be nothing. Summation, how we will do? Integration of dE. So this is nothing but integration of P dt. So for some duration of time, a current will be flowing or some charges will be moving. So for that stipulated time, how much is the energy? How much is the energy that is dissipated across the resistor? We can find. So this formula is always valid. This formula is always valid. Okay, so I square RT, V square by R into T, that also will be coming from here, but need not be always true. Okay, so note it down. Okay, so E is equal to integral P dt. Suppose P is equal to I square R. Okay, I square R. Now E is equal to integral I square R into dt. Now which all values we can take out? Those values which are constant we can take out of the integration. Those values which are constant we can take out. Those values which are not constant, which are varying with the time, we will have to keep it inside and integrate. So here E is equal to I square R I can take out. When I do integral dt, I will be getting E is equal to I square RT. But on what condition? I told you, whichever things are constant, those things we can take out. So if I is equal to constant and R generally we consider as constant. So I is constant, that is when current is constant, we can use this formula. If current is not constant, we will have to keep this I inside and integrate. Okay, so this is true. Okay, so this thing we can do. One condition I am writing here, when I is constant. When I is constant. Thus this formula is true when current is constant. Okay, so if we are really sharp, you may ask like DC current is always constant. You may ask direct current is always a constant current. Direct current need not be constant. You might be asking direct current is constant, and some of you, if you have some idea about alternating current, you might be asking like AC will be changing but DC is constant. Okay, AC will be changing, no doubt in that. DC need not be constant. DC is that type of current which will not change its direction. Okay, AC will change its direction. DC will not change its direction. So a current which need not be constant, which is not constant, but if it is not changing the direction, they are also what? Direct current. So direct current need not be constant. That is the point which I am trying to tell here. Okay. Suppose same thing, E is equal to integral P dt. Suppose power, if we are writing V square by R, then E is equal to integral V square by R into dt. So again same thing, if V square, if voltage is constant, I can take out, I can do, and energy will be what? V square by R. If I integrate dt, I will be getting T. So this can be used if V is constant. If V is not constant, then we will have to integrate. Clear? So condition is there, V must be constant. Here again, suppose if power P is equal to VI, we substitute E is equal to integral VI dt. So I can take VI outside, integral dt. So this is going to be VI t, but with one condition, V and I what are constants. Then this formula is valid. Okay, so these three formulas are valid if their respective voltage, current, whatever we are using, if they are constant. So take this question: find the energy dissipated in the resistor in 2 seconds. Okay, so if this is the resistance, current is passing through this, let's say this is 3 ampere and this resistance is equal to 2 ohm. Okay, 3 ampere is passing through this 2 ohm resistance. What is the energy dissipated? Okay, you will be asking me, sir, are you teasing us? So simple question. Okay, simple question only, just for concept building. We will do a small change in the question now. Now what is the answer here? Okay, energy 3 ampere current. So this is constant. This is constant, right? So I square R into T. So just if we put the basic formula, integration of P dt. So integration of I square R dt. So since this is constant, what we can do, I square R integral dt. When we do all that, what we got, I square R into T. So just for understanding purpose I wrote. Now if we see the current is constant, directly we can apply the formula. So 3 square into R is nothing but 2, time is given as 2. So this is how much? 9 into 4, 36 joule. So this is the answer here. Clear? Now we will do a small change in the question. Okay. Okay students, now take this question. Find the energies, okay, dissipated in the resistor in 2 seconds. I is equal to 2T, resistor is 3 ohm. Okay, what is the energy dissipated? Now here the current is not constant. So current is given as 2T. 2T means, what is this T? Time. When T is equal to 0, current is 0. When T is equal to 1, current is 2. When T is equal to 2, current is 4. When T is equal to 3, current is 6. So that is why an equation I is equal to 2T. Okay, so current is not constant in this case. Current is varying. So the real definition of energy is integral P dt. Current is what is given here. So integration of I square R dt. So integral I is nothing but 2T all square. R is what? 3 dt. Integration limits, what we should put? Energy dissipated in the resistor in 2 seconds. So 0 to 2. Okay. So 0 to 2, this is 4T square into 3 dt. So this term, that will be 4 into 3, 12, we will take outside, that is constant. And integration of 0 to 2 T square dt. So 12 into T cube divided by 3, putting the limits from 0 to 2. So 12 into, when you substitute this, we will be getting 8 by 3. Okay, so if we cancel this, we will be getting 4. So 32 joule. 32 joule is the answer. Okay. So simple question, just finding the energy dissipated in the resistor in 2 seconds. Only change that happened here is current becomes 2T. Okay, so entire process will change. So remember this formula. This is 100% valid every time. Clear? So E is equal to P into T. E is equal to I square RT. E is equal to V square by R into T. E is equal to VIT. So all these cases are valid when I, V, they are constant. 90% of the cases we get in this way. But E is equal to integration of P dt. This is what is 100%, okay, 100% applicable anywhere. Okay, this we will not do mistake if we follow this. So if we come to know that either I, V, anywhere which is changing, and if we are getting in the form of an equation of time like 2t, I is equal to 2t, or V is equal to 4t square, something like this, or I is equal to 2t plus 1, in this kind of equations always use this method, integrate it and get the answer. Clear? Take this question, students. This is 2019 JEE main. Okay, they asked this question in 2019 for JEE main. Okay, two equal resistances when connected in series to a battery consume electric power of 60 watts. If these resistances are now connected in parallel combination to the same battery, the electric power consumed will be, okay, two resistances when connected in series to a battery consumed power of 60 watt. Same resistances connected in parallel and connected to the same battery, what will be the electric power consumed? That is the question. Okay, so pause the screen, dear children. Okay, pause the screen and try yourself. Okay, I believe you are sitting with the book, pen, everything. That is how you should watch the lecture. Should not watch just normal videos. It will be completely waste of time. It is going to be like that. Okay, so get away from all the disturbances. Okay, sit with a posture, proper posture. Okay, in a proper table, proper seat. Then sit with the book and pen. Then concentrate on the lecture. Something if you don't understand, pause the screen, go back, re-see it again. Okay, if the lecture duration is for 1 hour, you just need to finish it in 1.5 hours. Okay, so see this peacefully, understand and proceed so that you can save time later, right? Fine. So pause the screen and do. Okay, I hope you are ready with the answer. So two resistances, two equal resistances, so R and R I am taking, connected to a battery, suppose this is V. So they consumed electric power of 60 watt. Okay, then same resistances connected in parallel to the same battery B, R. Now how much will be the electric power consumed? So in this case the R equivalent is nothing but 2R. So power P1 is nothing but V square by 2R. So this power is already given. So we can say 60 watts is equal to V square by 2R. Okay, so is it visible? Yes. Now in this case R equivalent is nothing but R by 2. So power P is equal to V square by R, just say P2. So P2 is here, V square by this R equivalent, divided by what? R by 2. We can say P2 is 2 V square by R. Okay, so two powers are ready. What we will do, just to divide P1 by P2. So 60 by P2 is equal to V square by 2R divided by 2V square by R. So here P2 is equal to this V square will be cancelled, this R will be cancelled off. We will be getting 60 by P2 is equal to 1 by 4. So P2 is nothing but 60 into 4, which is the answer will be nothing but 60 into 4, 240. So C, 240 watt is the answer. Take this question, students. The resistant network shown below is connected to a DC source of 16 volt. So this is 16 volt. The power consumed by the network is 4 watt. The entire circuit consumes this 4 watt power. What is the value of R? This is what is the question. They asked this question in JEE 2019. So the power consumed by the network is 4 watt, means this battery will be supplying 4 watt. Okay, energy will be supplied, power will be supplied. That energy will be dissipated or will be absorbed by here. So the power consumed by this whole resistance setup is what is 4 watt. Okay, so pause the screen and do it by yourself. Right, done. So here power is equal to V square by R we will use. So what is R equivalent? What is the equivalent resistance in this case? So 4 and 4R are parallel. This is nothing but 2R. This is R. 6R into 12. So 6 into 12 by 6 plus 12. If we do, what we will be getting? This is going to be 18. So 12 into 6. So this is going to be 4R and this is R. So the circuit which we are going to get is, this is 8R, this is 16 volt. Okay, so power P is equal to, which is given 4 watt, is nothing but V square 16 square divided by R equivalent. So that is 8R. So R is equal to 16 square divided by 4 into 8. Okay, so 116 to this is 4, this is going to be 8 ohm. So B is the answer. Clear? Understood? Okay, children. So we need again some maybe 1 or 2 more lecture on this power and energy. Power rating is there, and there are a lot of different varieties of problem that we can get from previous year questions. So that we will be doing in the coming sessions. Okay, so revise this, understand it, okay, and try to solve some more questions of similar type from any book of your choice. Okay students, thank you, goodbye.